Okay. We're moving on to enthalpy. Is it warm in here?
Yes.
It feels like, right? Why isn't this guy on? Okay, enthalpy. So we're going to get into some new terminology, but pretty much all we're really going to be talking about are reactions that, heat up when they happen. Is it possible, Jacqueline, for a reaction to get colder instead of hotter? It sounds like it sounds like a ball rolling up a hill. It sounds unnatural, doesn't it? But those health packs or whatever, those cold packs, don't you have to snap something and then you put it on wherever it hurts? So there's going to be reactions. Now, they're not very common, right? They're pretty much rare, but they will, if you mix the right stuff, they'll produce, reactants will go to product just like normal, but they get colder. And it's kind of going against nature, but it works. So it is natural. It is nature. So being able to know how much heat's going to be produced or react, or going to react, things are going to get colder, is key. It's important. Otherwise, things could really get out of hand fast. Okay. Let's see. Okay, so the book wants us to talk about kinetic energy before we start getting into enthalpy, which is a fancy word for heat in a reaction. Kinetic energy. Okay, some units. Now, Christian, in our English system, the unit for energy is on a Snickers bar. What is it? Yeah. It's on that little label. Everyone's worried about this. Calories, right? Okay. Well, we're the weirdos, Jessica. We're the only dudes in this planet. I don't even think the Brits use calories anymore, but they might. I never got out of... Heck, I got out of Minnesota and I'm here, but I've never got out of those two states, so I don't know what they use in Britain, but Jessica, everywhere else in the world, they use what for unit? Joules. Big J. That's what you're supposed to use for energy. Joules. Big J. A Joule. But we're never going to write that. We're just write big J for the unit. Now, to get the kinetic energy of a single molecule, you can calculate it. It's 1/2 mv squared. Erica, if we use the right units, we should get joules for kinetic energy. What units do you have to use for mass for this to work? The mass of that one single molecule. Erica, what do you have to use? Does anybody know? My physics people who had physics, kilograms. Oh, she remembers. This has to be in kg, kilograms. That's the weird. I think this is the only weird part about the metric system. Usually it's just so straightforward. But why kilograms? Why not grams? It's kind of weird. But that's how it is. That has to be in kilograms. Now the other one kind of is more straightforward, Yvette. The speed. Well, you have to square the speed of the molecule, but what units do you have to use for speed? Anyone remember? Physics people? Distance over time, which needs to be what unit over what unit? In the metric system. Meters per second. Right? And then you got to square it. Right? Well, then you got to square it, right? But the point is, it has to be meters per second. So in these problems, if they want you to calculate the kinetic energy of a single molecule, Yesenia, you need to multiply the mass of that molecule times its speed squared, just make sure the units are right. The question really is, how do you get the mass of one single molecule? There's a trick to it. Does anyone remember? The mass of one single molecule, of anything. You found its molar mass, and what do you do with Avogadro's? Multiply or divide the molar mass by Avogadro? Divide. because the molar mass was the mass of Avogadro's number. So if you want the mass of 1, just divide it by Avogadro. So this guy, really how you get that little m, right? Take the molecular weight and divide it by, how do you spell Avogadro? Avogadro. Right? Okay, so, and make sure the units are in kilograms. You're going to have to convert, because molar mass is in grams. Yeah. Okay, so now let's, we have to talk, here's a little movie. Transition states and activation energy. I think that is this one, but I don't have my sound hooked up. I'm going to need sound. For it being so cold outside, it's weird that it's hot in here. I think they turned on the heat, right? I bet you it's killing you in those dorms. Isn't it really hot in there? No? Okay. Transition states is this one.
Let's analyze the changes that occur in energy and atomic arrangements as the reaction between nitric oxide and ozone occurs. Initially,
Okay. Do you recognize which one's nitric oxide and which one's ozone? These molecules? Yeah, the red one's ozone. Ozone is actually O3, 3 oxygen atoms stuck together. You see this a lot around, well, you can't see it. You can smell it a lot around those big electrical transformers. It generates ozone. It's a pollutant. It's not good for the environment. And the other one, another pollutant, nitrous oxide. Okay, so they're going to show these guys, those are our reactants.
nitric oxide and ozone molecules are separated and are not reacting. The forward reaction proceeding from reactants to products is exothermic by 199.8 kilojoules per mole. Let's see how the energy changes and the molecular changes correspond. As the reactants approach, their energy increases. When the molecules...
Okay, I just wanted to... Oh, no, let's let you do the whole thing.
Transition state or activated complex, their potential energy is at a maximum. As the transition state is passed and the molecules become more like products, the potential energy decreases. Finally, the molecules reach the energy state character.
Do you recognize what it made? NO2, right? It looks like the shape of water, though, doesn't it? Okay. Now, one thing I wanted to point out, they have some terminology in there, and one of them was a what state?
Activated complex.
A transition state. And I really wish they had this a little bit more natural-like. Because these guys, they're colliding all the time, a gazillion collisions, but hardly any of them are in the transition state, meaning that they have to collide at just the right orientation with the right amount of energy, which is really extra than the other molecules, a little bit higher, and then they'll form product. So not every collision works. That's what they call the transition state, a specific orientation with a certain energy. Okay? And then they also use the word exothermic, meaning that this thing is going to give off heat or react with heat. It's give off. There's a couple hints. One is, see, this scales energy. So you're starting out way up here, you're ending up way down here. So here's the energy for all the reactants, here's the energy for all the products. Well, where'd this energy go? It's just the H word, heat. So that's where all that energy went. Just it heats everything up, heats up the surroundings. Okay. So. Okay, that was that one. Okay, so now we need to. The homework is going to have you plot this stuff, so you should really know how to reproduce this kind of plot. Be able to make it. Be able to label the coordinates, energy and reaction coordinate. Okay. Now, it would help to know what reaction coordinate is. Gloriana, in the movie, they kind of showed what reaction coordinate is, but what is it? All right, because it kind of progressed along the reaction coordinate. It's just a fancy word for what, probably? It could be, anybody help her? it could be time, because as this reaction progresses. But they really want it to be something with XY, some distance between the two reactants. But there's no zero along here. I wish there was, but there isn't. Right? But that's how it is. So it's just as the reaction progresses. So the reaction coordinate, you start out, there's the beginning of the reaction. Right? The reaction starts. And it ends. Well, they don't like, there's no job security in saying the reaction starts and ends. So reaction coordinate. So in the plots to the right, which describes an endothermic reaction and which describes an exothermic reaction? Gloria. The blue one is a, which one? Exothermic. Yeah, exo. The only way I can remember this is exit, exo, gives off heat. Heat leaves. That's otherwise I would screw these up every single time. So exothermic is the blue one. That means the green one must be endothermic, the one that's rare, right? Where, see how to get to, in the endothermic one, to convert into a product on the green one, you have to go up. You end up with more energy. So where did it come from? It has to suck up heat from the surroundings. So heat is an actually reactant. Okay. Are most reactions endo or exo? What would you think, Ashlyn? Exo, right? Almost everything's exothermic. Almost everything gets more messy, right? Hotter. Okay. EA is energy of activation. They had us labeled the transition states. Remember, that's that specific orientation that the guys had to collide with, right? And those are the transition states, this really weird geometry of these two guys stuck together just the instant before they turn into product. But the energy of activation is just the energy between the reactants and that transition state. The energy, it's kind of key because if these reactants don't get that energy, they can't turn into product. That's all it is. Energy of activation is the hump you got to get over to turn into a product. The energy hump, right? It's the energy hump you have to get over to turn into a product. And it's important because they don't just slide down a hill. You actually kind of have to go up a hill first before you can go down the hill, in that sense. Okay? Does that make sense? So if a quiz or a homework question says, sketch the energy diagram, right, or the potential energy diagram. This is really potential energy. Sketch the potential energy diagram of this reaction, right? You're going to put the reactants where it says reactants, and the products where it says products. If it's exothermic, make sure you put the products at a lower energy than the reactants. Leave a little hump for the energy of activation. And make sure you label the x-axis as reaction coordinate, right? So just be able to reproduce that, because I'm sure the homework is going to have you do that. It could be on a quiz, right? Okay, let's take a look at another show here. A thermite reaction movie. Yep. Oh, I just changed that about just before class. You know what Jessica's talking about? Starting products in on your chart. Let me show Stephanie. What Jessica's talking about versus starting products. I just changed it to reactants. I just noticed that this morning. I mean, you can use the word starting products, but that's not how we speak. All right, so I changed it. Okay.
Aluminum metal is a very strong reducing agent. The flower pot contains thermite, a mixture of finely ground aluminum metal and iron 3 oxide, plus a starter mixture containing magnesium metal. The reaction is initiated by igniting the magnesium metal ribbon.
So isn't that weird that metal can burn in the first place? I would not want to work in a magnesium metal factory. It burns, right? It burns bright. So definitely, Victoria, an endothermic or exothermic reaction. exothermic.
Some of the molten iron has flowed out through the bottom of the flower pot into the bucket of sand.
Yeah, it went right through the dang pot. They use this, at least I think they used to, I don't know if they still do, to weld railroad tracks together. I guess it was just easy to do and anybody could do it. But okay. So label EA and delta H. Okay. So Janet, where would you draw arrows to label the EA, the energy of activation? Start where and go up to where? Start at the energy of activation is the hump you got to get over to turn into a product. It's a hint. Start where you start out, right? Somewhere around here, and go. That's always EA. Start out at the height where the reactants are, the energy where the reactants are, and then just draw an arrow up to however high you got to go, the hump, to convert it into a product. And then we're supposed to draw delta H. Victoria, again, delta H, Victoria, is just a fancy name for heat, but yeah, so between what and what? The reactant and the product. Just remember that. Delta H is always good between the reactant and the product, because that's the heat. In this case, it's heat given off. Let's see, the product stops right around here somewhere, right? That's that height, so that'd be my delta H. And they like to have a little RXN down there. Fine. Probably for what? Their RXN, Lauren, probably is, you don't need it, but I guess it looks good. For what? What is RXN probably short for? Reaction. It's reaction. I don't know why it has an X in there, but that's just convention. Okay. Here's some questions. So, do you want to go to the boards or do you want to stay where you're at? Fine. Okay. I'm going to pick on Desiree then. For the thermochemical equation above, are reactants or products at lower energy? Are reactants or products at lower energy? Is she right? She says products. There's only one way you can tell. All right, this guy right there. He's negative. So that means it's exo or endo? Everybody. It's an exo, right? Negative, exit, exo. So that means heat's given off. Well, if heat's given off, you have to end up, products have to be really low energy then, right? It's going to be just like this guy, right? Remember all that heat was generated? Exothermic, a negative delta H. So where's products? Here they are. Okay. So go ahead and see if you can answer the rest of those while I try to turn on the AC in the back here. I wonder why none of these are turning on. It must be over 72 in here. Oh, it's because there's thermometers on the outside of the room, right? On these AC units. It's measuring it as really cold outside, so it's not going to turn on. We're stuck then. That's fine. Oh, we can open a window. All right. Keep on trying to answer them. I'll open a window. Poor Maria's going to freeze, but we'll open it just a little bit. Oh, maybe not. Okay. Is the reaction endo or exo, everybody? It's exo because negative. Okay, C's is where things are getting interesting, I think. If 2 moles of aluminum react, what's the change in delta H? So when they ask for delta H, they want an answer in kilojoules. What's delta H? They want an answer in kilojoules. Okay? So, how do you do this? If 2 moles of aluminum react, that's kind of like dividing the reaction by 2. Well, if you divide the reaction by 2, you have to divide delta H by 2 also. So the answer should be negative 150. But that's probably going to get a lot more complicated than that. So we should probably just work it out. We're used to, we said 2 moles of aluminum. So all I need is a conversion factor. And moles of aluminum has to be where? On the bottom, otherwise it's not going to cancel. You see what the conversion factor is going to be using the reaction? How many moles of aluminum in the reaction? 4. So you put a 4 down there. And up top, I'll just put my negative 300 kilojoules. It works. Right? That's just what we said, negative 150. So the terminology is that this is a reaction. When you tap on a delta H, this is now a thermochemical equation. So it's just one more conversion factor is all. Okay, that's really all it is. If 1 mole of aluminum oxide is produced, what is the change in enthalpy? Well, do the same thing. I don't like doing stuff in my head. I end up usually screwing up. So what would be my conversion factor, Paulina? Yeah, for that bottom one. Let's see. There you go. On the bottom, 2. And on the top, yeah, the negative 300 kilojoules. All right. So again, I guess that's negative 150, I guess, is the answer. All right. How about E? E. 1 mole of O2 reacts. How much heat is released or absorbed? Monica Soto Ruiz? Where'd she go? There she is. What are they looking for? Yeah, the heat. Is the heat, I think the word is what, synonym? The same as delta, is it heat and delta H, are they the same thing? Yeah. So they're just saying the same question, right? And is it released or absorbed, right? Well, let's just do the question first. 1 mole of O2. We need our conversion factor. Where is it? 3 of those O2s for every negative 300. So we get a negative 100. So there's our Q. Q is just a fancy word for heat, or the fancy little symbol. Q and delta H are the same thing. Okay. And we're supposed to say it's either released or absorbed. Adelpho, it is released. Yeah, it's released. Okay. All right. Now you see the game they're playing here? An F. All right. 3 grams of aluminum. What's Q? Stephanie, have a game plan here? Yeah. Yeah, 4 moles of aluminum. We're okay. We just skipped one step. Do you see what she skipped? Convert grams to moles. That's okay. We can convert it here, right? Let's see. So how many grams of aluminum are there in a mole of aluminum? Oh, I can't see that. About, yeah, thanks. 26.98. 26.98. So see how it's okay? The grams of aluminum cancel. Moles of aluminum cancel. Oh my goodness. Yikes. 3 times 300. That's negative. Divide by 4. Divide by 26.98. About 8.3. Negative 8.3. Kilojoules. Don't forget those units. Okay. So it's not too bad. It's the same kind of thing we've been doing before, just that we have one more conversion factor to worry about. And that's the enthalpy, or heat, they like to call it. Okay. Where's this stuff coming from? Let's take a look at this. Given the below thermochemical equation, what is the delta H for this reaction? Okay. Now let's see if I can show you the game plan here. So here's the guy in blue is the reaction that we want to, given the below thermochemical, what is the delta H for each reaction? Oh, for each reaction. Oh, I see. Okay. So they're going to mess with this reaction. What did they do to the blue one to get A? Christina, what did they do to get A? What did they do to that blue reaction? Yeah, they just moved everything over. They flipped it, right? So if you flip it, what would be the delta H for this reaction? Anyone see the trick to this? It's going to be positive 300, because now it's kind of like this. I mean, you could write plus, Q because it's negative, and then if you flip the reaction, now Q would be over here. Well, now it's a reactant, so it has to be positive. Okay, but if you flip a reaction, just flip the sign on delta H, because you're switching it from reactant to product or product to reactant. Jacqueline, how about B? What did they do to that reaction? Yeah, didn't they multiplied through by 2. So probably, Bianca, what's going to be the new delta H? Exactly, negative 600. All right, Christian, what did they do to this one? Divided through by 2. Jessica, so the new delta H would probably be negative 150. All right, now what are they doing here? Erica, what did they do to D? Multiplied by 4, but they also flipped it. Okay, so Yesenia, they multiplied by 4, and they flipped it. So positive 1200. That's the game we're playing. Exactly. I think you got the idea. Okay, so that's the manipulations that you can do with delta H if you mess with the reaction. Good. Okay. EX3. In this one, they want us to write a thermochemical equation. So remember, that's just a delta H, but you have to, that's just a reaction, but you have to list a delta H for it. That's a thermochemical equation. Okay, so Gloria, if it's a reaction, all right, there it is. That's our thermochemical equation. right? Gloria? We just have to identify the reactants, identify the products, make sure it's nice and balanced, and then write down our number for delta H. So do you recognize what one of them could be? Okay, that's going to go on the left side. So iron metal. I guess we should write an S. Right? It says just one, so we're going to leave a 1 there. Ashlyn, something else? HCl. It's going to be a reactant or product? Reactant. Okay. Janet. H, the H, hydrogen gas. That is going to be a reactant or a product. Product. Now the trick with hydrogen or oxygen or nitrogen gases, they're all 2s, diatomic. Yeah. Okay. Keep going, Victoria. Yeah, so how do you write iron 2 chloride? Yeah? There's a 2. I'll give you, I'm just trying to confuse you. There you go. And it says aqueous, so we should probably be nice. All acids are aqueous there, right? Remember that? Okay, I don't know if we're balanced. Lauren, are we balanced? Iron's okay. 2 in front of the HCl. Then we're good to go. Okay, there's one more thing we need to do here, Desiree, to make this a complete thermochemical equation. Is what? Yeah, so what are you going to put in for it? 87.9. Now remember, you have to attach the sign, though. It's either positive or negative, and you have to put that in yourself, Taylor. Which one is it going to be? It's negative, because heat evolves, right? It's producing heat. Good. There's our thermochemical equation, nice and balanced. Okay. Okay. Paulina. Let's, well, this one's not so bad. Let's jump down to EX5. I think that's harder. Right? Because then you recognize EX4, all you're going to do is just multiply through by 4, right? Do you see how to do that? In EX4, just multiply through by 4. Make sure you multiply the delta H by 4, and you're done. How about this one? I think is a good one. I think that. We have the average speed of a chlorine dioxide molecule is 360 meters per second. What's the kinetic energy? Okay. Use the equation. Excellent idea. 1/2 mv squared. Okay. So, is the speed in the right units? Monica Soto Ruiz? Or do I have to do some converting there? Yeah, we just got to square it is all. It's already in meters per second. I guess we could write this. 1/2 360. Gotta square it. What are we going to plug in Adelpho for little m? The ClO2. How are you going to get it? Periodic table. So we're going to find its molar mass. Then don't forget to divide by everybody? Avogadro. All right, so let's find its molar mass. Chlorine is like 35.45 plus 32 So you get around like 67.45, right? So we said little m, divide the molecular weight by Avogadro's number, right? So little m, 67.45 all over 6.022 times 10 to the 23rd. I guess if you want to see the units, grams per mole, so our per moles are going to cancel. But let's see here, 67.45. Divide that by 6.022, 10 to the 23rd. I get about 1.12 times 10 to the negative 22. Okay, so Stephanie, just plug and chug. Something wrong. We gotta convert it to kilograms, right? Otherwise you're not gonna get what unit for energy? Joules. So we gotta convert to kilograms. How many grams in a kilogram, Christina? What was that number? You want to remember? 1,000. 1,000 G's in a kg. So I'm going to end up with 1.12 times 10 to the negative 25 kilograms. Now I can plug that in up here. And get an answer. All right? Don't forget to square the 360. About 7.2 times 10 to the negative 21. It's supposed to be a 7. 7.2 times 10 to the negative 21 joules. Okay. That makes sense? I think the trick to doing this, since I gave you all the equations, just remembering little m is molecular weight over the Avogadro. Okay. So you have 5 minutes. See if you can knock these two out. And then I think you can knock these two out, you'll be totally ready to do the homework. You can work with folks around you. Yep. Oh, the final answer? Yeah. Yep. Mm-hmm.
Can you explain why we have to put a 2 before the H's?
There's only, you have to take it on faith.
Okay.
You have to take it, because there's no way that you would know. And that's just how this thing exists in nature. Just like oxygen is O2. There's no way that you would know. You just have to take it on faith.
So it's hydrogen, oxygen, what else?
Hydrogen, pretty much all of them. Every single gas except the nobles. So nitrogen, and all those guys that are gases: nitrogen, oxygen, fluorine, chlorine. Right? They're all diatomic. Hydrogen. Just the nobles, they're the only ones that are just sitting there by themselves. So in number 6, you don't need to write a reaction or anything like that. You just have to, right? The answer is either going to be plus or it's going to be negative. And then here the answer is going to be warm or cold. So that's all you have to do for EX6. It's going to be what for the sign? Positive, right? Because it's getting, endothermic. It's endothermic. So that means the flask is going to get cold. Very odd. Rare. But it happens. You've got some converting to do for number 7. You have the English system to thank. We're the only dudes who use grains and feet. A couple more minutes. See if we can get started on 7. Knock it out. Oh, I mean turn the lights. Or push the on button. Yeah, there's solar. Sorry. I'm getting more and more calculators. I think folks are losing them. So if you're missing one.